So I think we're just gonna make a start at this time. This is a recording from my optional live online session for BIO201 on Wednesday morning. Like I've said before, I realize that we all have very busy schedules. So I totally understand that there are times when people are not able to join. This course is asynchronous course, so there's no requirement whatsoever of being somewhere at the particular time. But I still think that these sessions offer some value for us to get together or have an opportunity to get together for anyone who wants to have more synchronous, immediate interaction. I'm also going to be recording this session for the benefit of anyone who might want to visit this session a little bit later and check what was covered. Really, these sessions are meant for giving space and an opportunity for anyone who has questions to get those questions addressed. But also, if there's not a high volume of specific points that students want addressed, a lot of the time during these sessions, I use this as a chance to provide kind of a nutshell version of what we've covered that week. So kind of a crash course on the lecture material. So it is week 3 of our course. We're really kind of getting to it and making good progress and getting to the rhythm of things after first couple of weeks. So I really appreciate you being part of this course, and I really appreciate your continuous hard work on this course. This week kind of aligns with what we did last week. Last week, we looked at various different tissue types and how that relates to the anatomy and physiology. And this week, our focus is on some of the basic concepts when it comes to the kind of having a shared ground or shared understanding where we're building up from as we move on our course of anatomy and physiology to various different specific systems. So I assume that a lot of the topics that we will be covering this week are familiar. This is more of a revision opportunity, an opportunity to make sure, like I said, that we all have a shared understanding of core concepts in biology. So this week we focus on basic chemistry behind the the life behind living organisms. We'll talk a little bit about cells, for example, and depending on how time allows us, we'll also talk a little bit about the genetics. So it's really to ensure that we are all set for success when next week we will move on to our very first system of the body, which is going to be the integumentary system. So we'll be having a look of the skin and associated structures such as glands, nails, hair, and so on. So this week kind of wraps up this getting you set for success of the first couple of weeks. Here's a really brief kind of plan for what I was intending to do today during this session. I just think it's always important that we have a chance to connect with each other, check how things are going. And even if you're not able to join me today in a synchronous setting, remember that I'm always interested and I'm always curious to hear how you are doing and what can I do to help you to reach all the goals that you have for this course. I wanted to mention a couple of words about these optional meetings. I wanted to highlight what are the homework assignments that I'm looking for you to submit for this week, and then provide probably most of the time together, at least on this recording, is going to be dedicated on providing a summary of the key concepts that you need to know about the lecture material. Depending on how timelines go, we might also venture a little bit to having a look of what's going on with the homework for this week in terms of actually looking at questions that might come up. So, like I said, I think it's always important to acknowledge and realize that we all wear many hats, we have many roles, and this course is just part of that bigger puzzle. So it is important for me to know if there's something that you feel that is especially exciting that's going on, or if there's something that might be adding an added level of challenges when you're navigating through this course. Do not hesitate to let me know. I am here to assist you in every way that I can so that you can reach all of your goals for this course. And if it means that we need to figure out alternative ways in terms of timelines and so on, all you have to do is let me know and we can discuss what can we as an institution do to help you to succeed. I think it's also important that we celebrate successes and we celebrate things that are going well. Recently, I've been spending some time also on my face-to-face classes on this kind of taking the time at the very beginning of some of our classes to just kind of look inwards, do a little bit of a self-care, have an idea that we all share and consider for each meeting. I think we're living a very fast-paced life at the moment now that we're coming out of the pandemic. And it seems like even though we had, in a way, a little bit of a slowdown, now everything's going on at twice the speed of things that we were doing before, and everyone has even more responsibilities. So please know that I realize that, I appreciate you, and I think that I want you to know that I'm on your side. It's really important for me to help you with whatever you want to get out of this course. Like I've mentioned before, I'm trying now initially during the early part of this course, offering these live online sessions twice a week. They're going to be on Wednesdays, now in the morning, and then in the afternoon again. I will always record these. If the material is very, very, very similar on these two sessions, there is a chance that I only upload one recording if no one shows up to the second session. There's no point of me going through the same monologue by myself, but I will always have at least one recording available for you. Remember that this is not the only time when you have access to me, though. I do offer office hours. I also am more than happy to set a time if you want to have this kind of synchronous interaction. If you reach out to me through Canvas messages, we will figure out a time that works for both of us. And if you don't need synchronous, immediate interaction, you can always drop me a message through Canvas and I can help in writing as well. So I think that that's what I had to say about that. Let's have a look of this week's material. This week, I have actually, even though we're covering 3 chapters, I have decided that we're focusing on doing a quiz on 2 chapters. So we're doing a quiz on chapter 2 and quiz on chapter 3. Both quizzes contain a bunch of questions that relate to the lecture material. Your textbook is always the primary source of information, but I offer pre-recorded lecture videos on your Canvas course. I offer a bunch of handouts this week, for example, that might come in useful. And then I offer these review sessions. Question answers to those quiz questions should come visible from the textbook, should become clear from the textbook, and these other sources are there to assist you. You will be completing these quizzes as you've been completing so far, still on Connect, which then links those grades to our gradebook on the Canvas, but you can access the quizzes simply from the Canvas by clicking the quiz under the heading of homework for this week. I had also mentioned on this slide what's happening next week. So next week is the first actual chapter in terms of a body system. And the body system that we're looking at was the integumentary system. So we'll start with that. And in addition to having a quiz and practice anatomy for that, we will also have a kind of a more of an application-based question that allows you to apply what you're learning about the material in a little bit of a different way than what we've done before. So I'll talk all about that next week and also on my weekly announcements of summarizing what's coming up on the week at the beginning of the next week. Sometimes students are already looking into the future and thinking about the tests that you have. We're still a little way away from our first test, but just to give you an idea, I want to be very transparent. I want to be very clear. For the first exam, we're covering chapters 1, 6, and 7. So we're covering that very first chapter where we learned about the language of medicine. We learned about directional terminology. We learned about body planes. We learned about many essential concepts. I will not be testing you on last week's material or this week's material in the tests. We will simply cover those on a weekly homework because I think last week and this week really is just revision. So you've been tested on those before in your previous courses. So exam will include also the material on the integumentary system, which is our next week content. And then on a chapter that's kind of an introduction to the skeletal system. So when we start talking about cartilages, we're starting to talk about introduction to the bone. So those are the chapters that we'll cover for the first exam that we'll take together. Same goes for the practical. Practical is heavily based on those practice anatomy assignments that you will have completed. Exam is more based on the quiz questions that you will have completed. But like I said, I will provide you full introduction to what to expect when it's a week when we're completing exams at that time. You do not need to worry about it just now, but I just wanted to be very, very transparent and very clear of how I'm envisioning these revision weeks, last week and this week, to fit into the bigger picture. But for this week, please make sure that you submit the quizzes 2 and 3 for chapters 2 and 3 by the end of this week. I believe it's going to be 10th in terms of the days. 1 minute before midnight is when the quizzes close. If you ever miss a quiz, if you ever miss another activity that's your homework activity, I would encourage you to reach out to me. I will try to work with you to see if there's an opportunity that you could have the due date extended so you're able to still collect those points towards your final score for this course. So without a further ado, let's talk about the material that we see on this week's study material. And we'll start by talking about chemistry. And chemistry really is the field of science where we're really focusing on the small stuff that life is built on. Sometimes my students are like, well, I thought I'm going to take a biology class. Why do I find myself now in a chemistry class? And the answer to that really is that everything in life is made of chemical building blocks. So atoms that can then join to molecules, and we're seeing also these connections between different atoms as they're forming these molecules, and so on and so on. So we need to have that understanding of the small stuff before we can start building up towards larger scale structures and organs and eventually organisms. And then biology would continue even bigger scale, where you could look at interactions of organisms and so on. But for us, for anatomy and physiology, it is important to have just a very basic appreciation of the very, very basics of the small stuff that makes us up. So really understanding those chemical bases will help us to understand them, what we're all made of, the structural properties, how different things interact with each other when we're looking on a chemical scale. We'll see that a lot when we talk about the physiology and physiological reactions on a smaller scale, and so on and so on. What I wanted to do really to start with was to highlight how really in living organisms, there's really four main um elements that we end up seeing that organisms are made of. So carbon and hydrogen are often considered as the kind of backbone of life. So we often talk about hydrocarbon uh, structures, and then this forms the foundation of a lot of things that we'll then see that there's added functional groups and added variation, and as such also nitrogen and oxygen are seen in great quantities in living organisms, and together these four substances form about 96% of all living organisms. So you'll see that understanding, especially these elements, becomes important as we're trying to understand life, and we're trying to understand how the basic building, understand the basic building blocks behind the anatomy and physiology. Some of the terms that I want to make sure that we feel kind of comfortable with as we're covering those, we will see that the term matter refers to anything that has two properties that we'll see. First of all, if something's matter, it has a mass. And sometimes students ask me what's the difference between mass and a weight. Well, weight is dependent on the gravity where we're at, whereas mass is more of a kind of a more universal concept. The mass of an object will be same regardless of the gravity. So if you prefer, if you find it confusing, you can consider in this context that mass and weight are almost analogous. So if something's matter, it has a weight or it has a mass, if we're being more precise. In addition, matter tends to take up space in the universe. So it has some sort of a volume. And the example that I've used on this slide, as you can see, is this marker. So markers, for example, we know that this is a piece of matter. It's a real thing that exists because it has this mass and it takes up space in our surroundings. Let's continue our discussion. When we think of the matter, another thing that we sometimes see that matter can take different forms. So I think one example that often gets used is, for example, water. Water can take solid form as ice. It can take a liquid form as we see it, for example, for when we drink water from the cup. It can take also a gaseous form, vaporous form. So we have that water vapor that can also be a form how we see water taking. There is a fourth form, not so much for water, but certain other elements that we'll sometimes see, which is a form of a plasma. I'll leave that discussion for your other classes, but just for the sake of completedness, I did want to acknowledge that that also exists. So now that we know what matter is, let's take this concept a little bit further and talk about substances that we find in our surroundings, and substances that we consider as natural substances that we cannot break down further, at least not with natural easy means. Some of the elements that we do have, we can break down further, but that takes a little bit more effort. That's more complex. We have to often do it in a lab setting. So for our purposes, an element is something pure that we find around us. That is the simplest form that we can make it. And really, what we end up noticing that all life and all matter is made of different elements. So you've seen probably periodic table of elements, which is used to list different elements that we find around us. And this periodic table of element has been revised quite a few times throughout the history. So there's been different versions, and as we identify new elements, they get included. But this periodic table of elements is not just a random one, random listing elements however someone has felt. There's actually a lot of thought behind the order and organization of a periodic table of elements. The listing is very precise because where in the periodic table of elements these elements are placed holds a specific meaning and specific importance. And we'll come back to that point in a little bit later. We'll notice that there's 92 naturally occurring elements at the moment included. There's 26 orders that we can actually generate in the lab setting. And when we look at a periodic table of elements, rather than just seeing the elements listed with their abbreviations, we can get a lot of other information out of here. So often it includes a bunch of other data, and we'll have a look of that as well in just a few moments' time. But since we are talking about elements, I wanted to relate this to the concept of atoms. So sometimes there's some disconnect at what's the relationship between elements and atoms. Atoms are what everything is made of, and elements are the purest, the most simpler formats of matter that we find around ourselves. So often elements can be viewed as an atom, if that helps you to kind of draw that connection. We see that atoms are the smallest unit of matter that we can have, and all chemical elements are formed from atoms. So let's have a look of a diagram of what an atom would look like. And you've probably seen diagrams like this a lot of the time. So we have something known as nucleus for the atom, the very center of an atom, which contains subatomic particles known as protons and neutrons. Protons carry a positive charge, whereas neutrons, as the name proposes, are neutral in terms of their electrical charge. Around the nucleus, we have in atoms electrons that circle the nucleus. There can be a varying number of electrons depending on what atom we're looking at, but it's almost like they are little planets circling around the nucleus. And the arrangement of these electrons depends on how many we have of those. Electrons carry a negative charge. I do want to highlight when we look at these diagrams, and we'll see many different versions of diagrams that showcase the atoms, that remember these are oversimplifications. Life is always harder than where we start when we study life. Really, this is kind of like, you can consider it almost like as a diagrammatic snapshot at one time. In reality, these electrons would be circling around the nucleus on their plane, and they would not be just on this two-dimensional plane. They would be actually circling to all kinds of directions. So these diagrams are good for us gaining the basic understanding, starting point, but in reality, it is much more complex when we're trying to visualize atoms. So I mentioned earlier on that periodic table of elements often includes a lot of other information that you find other than just the atomic symbol, so the shorthand abbreviation, the name for that particular element that we see on the periodic table of elements, each box. In addition to that, we can see a bunch of other information listed there. For example, the atomic number and also the atomic mass. Now you might ask that, well, how do we come up with the atomic mass? Often referred also as a mass number of an element. Well, to calculate the atomic mass, mass number of an element, we add together the mass of protons and neutrons. So the mass of subatomic particles that forms the nucleus of an atom. So that is another number that we sometimes see. And one of the interesting things that we sometimes see is that this atomic mass can vary in terms of the number of neutrons. The number of protons remains the same, but the number of neutrons is different. However, neutrons' contribution to the mass is kind of a rather small. But when we're seeing the same atom, same elements, but we see different variations of that. When we're talking about different isotopes of that element or isotopes of that matter. So that's kind of where we're heading with this. And when we're talking about isotopes, one of the concepts that we'll definitely start thinking about is radioisotopes. So these are different isotopes of an element, and they contain really unstable combinations of neutrons and protons or excess energy in the nucleus. And that causes these radioisotopes have certain characteristics that we can actually utilize for beneficial uses. So a lot of medical imaging uses radioactive isotopes as trace for tracing or tracing of the passage of material to show where the blood flow is greatest. For example, in these functional MRI images that we're seeing here, we can also use radioisotope isotopes to define the age of an organic matter, age of an organic object. There is a decay rate that we can use then to calculate how far back into the history an object goes based on the radioisotope that we can then measure and use that to figure that out. Obviously, there's been also bad uses of radioactivity. I'll leave that outside this discussion. So earlier on, I mentioned that periodic table of elements really was a way for us to list all known elements and list them in a very specific manner. So what we'll end up seeing that periodic table of elements contains these columns, if you wish, and we call them periods. And in addition, they include these rows, if you wish, and we call them groups. And where, in relation to what period and what group an element falls on this table is going to be really important for us when we're trying to understand what kind of properties that element has. So a lot of the time, you'll end up seeing that people who work in the field of chemistry are able to predict a lot of reactions that will take place between different elements simply on their relative locations on the periodic table of elements. So it's kind of a handy tool in that sense. Now let's move a little bit to a little bit larger scale. And what we're seeing here, we see that atoms can join together. And as atoms join together, they form molecules. So this can be two atoms or more than two atoms that join together. And as they're joining together, they are held together by chemical bonds that these atoms form between each other. And typically, the overall electrical charge of a molecule ends up being neutral. So there might be charge differences between different parts that make up the molecule, but overall molecules typically end up being neutral. Let's look at these forming bonds and atoms coming together a little bit more as a concept. Well, when we have something that we describe as an electrically neutral atom, in an electrically neutral atom, we have the same number of electrons as we have the number of protons. Remember, electrons carry a negative charge, whereas protons carry a positive charge. So overall, the number of pluses and minuses on this atom is now going to be equal. So that's where it comes from that we call this particular atom that we see here as an illustration as an electrically neutral atom. be much more complex than what we saw on our previous illustrations. There can be a large number of electrons, but there is a specific order in how these electrons organize. The innermost electron shell that we have can only fit 2 electrons on it. If we have more than 2 electrons circling the nucleus of an atom, then we need to create a second electron shell. So this innermost electron shell will hold the maximum number of electrons that we had, which was 2 electrons. If we have more than 2 electrons, remaining electrons other than these 2 then move on to the second electron shell. And this second electron shell can hold up to 8 electrons. And we can move on to third and further electron shells based on the number of electrons that that particular atom has. So this leads us to realize that diagrams of atoms can get really confusing and really overwhelming very quickly. But we can simplify our life. And how we simplify our life is that we focus our attention on the outermost shell of an atom. And the reason why we focus on the outermost shell, which is also known as a valence shell of an atom, is that this outermost shell really defines the properties in terms of behavior of in various different chemical reactions that that particular atom has. Because in order for us to have the atom interacting with others, it's not these inner shells, it's the outermost shell that defines what happens. And we can have 2 kinds of situations, or multiple, more than 2, but we're going to look at 2 situations. We're going to look at a situation where the valence shell, so the outermost shell of an atom, holds maximum number of electrons. So when there's the maximum number of electrons on the atom's valence shell, the outermost shell, we talk about that particular atom being stable. And what I mean by that is that when we have an atom that has reached that stage, atoms always want to have a full valence shell. And when they have a full valence shell, they're not very reactive at all in terms of do chemical reactions and in terms of interacting with other atoms. So they're kind of in their happy place. They are very stable. They're not very reactive if they have a full valence shell. And obviously the valence shell that we look at, it can be any of the shells, but it is whatever happens to be the outermost shell for the particular atom. In this case, we're seeing a valence shell, which is the third electron shell in this diagram, and it contains the maximum number of electrons that can be fit into this third electron shell. So as a result, this particular atom is stable. It has a full valence shell. Let's look at another situation. We sometimes have atoms that are very close of getting a full valence shell, but they don't have it yet. One way how we could have an atom that's close of getting a full valence shell is that it only needs 1 additional electron. And if it received that 1 additional electron, now it would reach this happy state of having a full electron shell, the full valence shell, the outermost electron shell. Well, in this case, the easiest way how this particular atom that we're seeing here, where we have on the third electron shell, which is the valence shell of this atom, we have 7 electrons currently there. This atom is going to need only 1 additional electron, and it reaches that stage of being stable, having a full valence shell. So this particular atom is going to be very actively searching to reach this stage of being in their happy place. So these kinds of atoms are known to be very reactive. It could be that it doesn't just have to be 1 electron that this particular atom needs to gain. It could be that it has 6 and it needs to gain 2 more. So it would still remain very reactive. But reactive atoms, reactive elements, are just short of having that full valence shell. So a lot of the time it can be that they're just searching for a few more electrons. There's another way to be a reactive atom as well. In certain cases, all you would have to do is to get rid of one additional electron from your valence shell. And if you got rid of that, then the next shell underneath that becomes your new valence shell. And this new valence shell, which would be the second electron shell on this particular diagram, has the maximum number of electrons on it. So really what we're trying to do with this atom is to get rid of that one additional electron. So again, this atom is going to be highly reactive. It's actively searching ways to get rid of this electron so that it can reach its happy, stable state. And again, it doesn't just have to be one electron, it could be two electrons, but really what you'll see that some elements are very stable because they're in their happy place of having a full valence shell, full number of electrons on their valence shell, whereas other atoms, other elements are very reactive because they're so close of reaching that full valence shell. So they're actively searching for ways to accomplish that. So I hope that helped to clarify the difference between something being reactive or stable. In this picture, we're seeing the example now. If we got rid of that outer electron on the third shell, now we would have a full valence shell, and this atom would become stable. So knowing this, that atoms can either be stable or they can be very, very reactive. Actually, this concept can be seen also on our periodic table of elements, where we're seeing that certain elements listed on this table are found in the areas where these particular elements are very reactive. So if you have one of these elements, you know that it's going to be very, very eager to take part on chemical reactions. We also have elements that have that full valence shell, and if they have that full valence shell, these particular elements are very, very stable, so they don't tend to be reactive in chemical reactions most of the time. So again, simply by looking where different elements fall on the periodic table of elements gives us an idea of how reactive or how stable these elements are going to be. Now, let's think of this process where we had an atom that actively searched for this stage of being stable by getting rid of or gaining additional electrons. So this is really the foundation of what drives chemical reactions. In chemical reactions, what we're doing, we're rearranging things around so that all the participants, or as many of the participants as possible in this chemical reaction, get to the stage that's stable for them. So we're really aiming for that full valence shell. And here we saw an example of where for this particular atom, the way to accomplish that was either by getting rid of one electron, as we are seeing here, or it could be, in this case, gaining an additional electron. So when we have a chemical reaction, we often write it out. It can be a chemical shorthand or it can be a visual illustration as we're seeing here. But what we're seeing that there's something that's the starting point of that chemical reaction. So what goes in, where it all begins from. We talk about these being reactants of a chemical reaction. So what are the original substances? Then a lot of the time there is an arrow which tells that something happens. And as a result, we're left with the outcome of that chemical reaction. And what we're seeing listed as the outcome of that chemical reaction is going to be the products of that reaction. So we have reactants, what goes into the chemical reaction, then something happens, and out comes the products, what comes out of that chemical reaction. So that's really the kind of basic two terms that we need to know when we talk about chemical reactions. I have an example here. So what we're seeing here, we have a reaction where we have reactants that include two hydrogens and one oxygen. if you ever have two hydrogens and one oxygen together, they do tend to get together, form a molecule, and that molecule is now, in terms of its chemical formula, H2O, because there's two hydrogens and one oxygen all joined together. So rather than being individual elements or individual atoms, they join together to form a molecule. And this is, of course, our water molecule. So the water molecule would be the product of this chemical reaction, whereas the reactants were the two hydrogens and one oxygen. So you'll see that in chemical reactions, we talk about these terms, reactants and products, in relation to what goes in and what comes out of the reaction. Here's we have another type of an example. Here we have hydrogen peroxide, which is made of actually of a combination of hydrogens and oxygens. And what typically happens to hydrogen peroxide over time, if we just leave hydrogen peroxide in a beaker on a room temperature, is that these hydrogen peroxide molecules start breaking down over time, and they break down into water and oxygen. So if you have a jar of hydrogen peroxide and you leave it open in a room conditions, over time, the hydrogen peroxide will slowly start to turn into water and oxygen. So in this case, the reactants would be the hydrogen peroxides and the products would be the water and oxygen. This type of a reaction that we're seeing here is known as irreversible reaction, because by natural means, just in room temperature, room conditions, this reaction only proceeds one direction. So hydrogen peroxide turns into water and oxygen. It doesn't happen that just by having a jar of water and oxygen around it, it would spontaneously rearrange itself to become hydrogen peroxide. So this reaction has only one direction. Reactants turn into products. And it's a one-way irreversible reaction. We can have some reactions where this is not the case, where we can go both ways. So in this picture that we're seeing here, the reactants, so what goes into the chemical reaction, are a bicarbonate and a hydrogen. When bicarbonate and hydrogen have a chance to react with each other, so they're the reactants, they form a product that's carbonic acid. But it also can be that this product, that is our carbonic acid, can go back into being a bicarbonate and a hydrogen. So this reaction can go either way. We talk about this being a reversible reaction. So reactants become a product, but in also we can have a reaction the other way around, in which case this carbonic acid would be the reactant and it would become product of, that is, the bicarbonate and hydrogen. So it can move either way. We can flip this reaction back and forth. So for that reason, you'll see that this arrow is drawn as having two ends. So it is a reversible reaction. It can go both ways. We can have much more complex reactions. We can have reactions where we have multiple steps on our path to somewhere else. So bicarbonate and hydrogen, in order for them to become a carbon dioxide and water, they have to go through an intermediate step of becoming a carbonic acid, which can then become a carbon dioxide and water. Similarly, carbon dioxide and water can join to become carbonic acid, and which can then convert itself to bicarbonate hydrogen. So this is why these chemical reactions often appear kind of complex, because it's not always that there's just a reactants and products. There can be multiple steps between when the reactants become to a product. So they can be much more complex reactions that we end up finding. Now, let's think about these atoms forming molecules, since we have a basic appreciation of the chemical reactions a little bit further. And what I want to talk about as the very first thing is the different kinds of bonds that we can end up forming. And there's really three types of bonds that I want us to look at. And we're going to start by looking at covalent bonds. How I often describe covalent bonds to my students is that really sharing is caring. So when we have atoms that come together to form a molecule and how they're all able to accomplish that stable state, that happy state of having a full valence shell, a full outermost electron shell, is through sharing some of their electrons. We talk about there being covalent bonds between these different atoms. Let's have a look at that. So here we have two hydrogens and an oxygen, and we saw earlier on that there is a spontaneous tendency for these to come together. So the reactants are our hydrogens and oxygen. They come together and result in a product that's H2O. So it's a water molecule. And how they're able to accomplish this is that look at these hydrogens. Hydrogens have one electron on their outermost electron shell. What's the easiest way that they can reach their happy place is by adding one additional electron on each one's outermost electron shell. Oxygen instead, here we have 6 electrons on its outermost shell, so on its valence shell. In order to find that happy place for oxygen, really it needs 2 more electrons to reach that full valence shell. Well, if hydrogen wanted more electrons, oxygen wanted more electrons, we can't really just give away or gain because someone's going to end up really unhappy. What happens in this case? That actually neither one fully gets an additional electron, but rather they do sharing of some of the electrons. So this hydrogen, some of the time, it has 2 electrons on its outermost shell, and some of the time, this oxygen will have 8 electrons on its outermost shell. So they are sharing some electrons together in order to accomplish that happy state for everyone. And when we're talking in a chemical shorthand of sharing a pair of electrons, we typically symbolize it in our notes as a line that connects these two atoms together. So a line will symbolize to you in a chemical shorthand a covalent bond where 2 electrons are shared together. Single line tells us that 2 electrons are in that particular part of a molecule shared together as forming a covalent bond. What I did here, I kind of twisted around this diagram into more of an accurate representation what a water molecule looks like. It doesn't quite line up the way I had drawn it before. We can have also situations where we share more than just a pair of electrons. Here we have 2 oxygen atoms. Each one has 6 electrons on their outermost shell. If 2 oxygen atoms come together, one thing that they can do, they actually share 2 pairs of electrons together. And in this way, both oxygens, at least part of the time, have 8 electrons on their outermost shell. So now that we're sharing 2 pairs of electrons, we're drawing 2 lines between these particular atoms. So again, you're learning that chemical shorthand, that 2 lines in a chemical formula of a molecule will tell you that there's covalent bonds, and now rather than having just one pair, there's actually 2 pairs of electrons that are being shared between these atoms. Sometimes this sharing is equal. So the electrons spend as much time around both of these oxygen atoms that we're seeing. So it's a fair deal. Both of these oxygen atoms that we're seeing here have as much overall time having those shared electrons. So we talk about it being electrons being equally shared, which is known as nonpolar covalent. And the nonpolar just means really that it's an equal sharing of these electrons. Well, if you're following where I'm heading with this, we will have situations where this sharing of electrons is not always equal. So we don't always have a nonpolar covalent bond. Instead, we can have also polar covalent bonds. In polar covalent bonds, there is an unfair time, if you wish, or unequal time that these electron pairs, shared electrons, spend with different atoms. So overall, there is a difference how long of a time we see the electron spending with one versus another part of the particular molecule that we're seeing. So when electrons are shared unequally between the components that form the molecule, between the atoms that form the molecule, we talk about it being a polar covalent bond. Now let's have a look at ionic bonds a little bit. So in ionic bonds, we're not actually sharing electrons, but there's a complete movement of the electrons from one atom to another. And as there is a complete movement of electrons from one atom to another, there is an overall change in the total charge of that particular atom as a result of that. Either it's gaining an electron, which makes this atom more negatively charged, or it's losing an electron, which makes this atom overall more positively charged. This kind of a situation gives us a rise for ionic bonds, and let's have a look of this. So here we're seeing an atom that has 11 electrons in total. That means that on the innermost electron shell, it's going to have 2. On the second electron shell, it's going to have 8 electrons. And then there's going to be a third electron shell where it has 1 more electron. So that would be what we're dealing with here in particular with this sodium atom that we're seeing. So the ideal situation for this sodium would be if it was able to get rid of this one additional electron on its outermost electron shell, on its valence shell, because if it got rid of this additional electron that it has on its outermost electron shell, the valence shell, this valence shell would stop existing, and the revealed electron shell, the second electron shell, would now become its valence shell, and the second electron shell would be full. It would have a full 8 electrons, the maximum number that can fit into there. So currently, with having 1 electron on its valence shell, this sodium is going to be very, very reactive. But if it manages to get rid of this 1 electron, it becomes very stable because then it has this full valence shell. In comparison, we're seeing here chloride. With this chloride, it has 17 electrons in total. If we do the math, that means that there's going to be 2 electrons on the innermost shell. The second shell will also be full. It will include 8 electrons. So we have to create a third electron shell, and this third electron shell contains 7 electrons. That means that when you have 7 electrons and you're really striving for that full valence shell, and you have 7 electrons on your valence shell, the easiest way for this chloride to accomplish that would be by gaining an additional electron. If it gained an additional electron, it would now have a full valence shell. So what happens a lot of the time if you have sodium and chloride together in a chemical reaction? They do exactly what we just said that they want to do. Sodium gives away 1 electron, and chloride gains 1 electron. And both of them reach that state that we wanted to have, which was the happy state where they have the full valence shells. But remember, electrons carried a negative charge. Now, if we're giving away 1 electron from sodium, which was a balanced atom in a sense that it had an equal number as it had electrons. It had also a similar number of those positively charged particles um, on its nucleus. So as a result now, there's an overall slightly more positive charge with this sodium that we're seeing here. Similarly, chloride now gained an additional electron, which introduced an additional negative charge to this chloride atom. So overall, sodium became slightly positively charged and chloride became slightly negatively charged simply because of where though that one single electron with its negative charge moved to. Well, what we end up seeing that when we have this an atom that is slightly positively charged, we call it a cation. And when we have an atom that's slightly negatively charged, we call it an anion. So here's really what we just discussed. In ionic bonds, we're seeing that in order for these atoms to gain to their happy space, gain to that stable state, there is some movement of electrons. It doesn't have to be just one electron. It could be more than one. But I used an example of just movement of one electron to make our life easier. And if an atom loses an electron, so it loses one negative charge, it becomes overall more positively charged and it is a cation. If an atom accepts an electron, it becomes overall slightly negatively charged because we're now introducing that negative charge with that additional electron. So we call it an anion. So I think that that's a summary of what we just saw. And what we see is that pluses and minuses in life tend to attract each other, and that's how ionic bonds are formed. Final bond type that I wanted to talk about is a hydrogen bond. Hydrogen bond is really just kind of a special situation. And the reason why we're talking about this special situation is really because with the hydrogen bonds, we're talking about water molecules and we're talking about attractions of water molecules with other water molecules. Because water is really a fundamental basis of life. One of the things that we end up seeing is that there's going to be a special type of bond that we have dedicated for this attraction of water molecules with other water molecules, and this type of a bond is known as a hydrogen bond. Let's have a look of a hydrogen bond, what's going on there. So you remember that I mentioned earlier on that water molecule was a result of hydrogens and oxygen forming a molecule where we had unequal sharing of electrons. So these hydrogens and oxygen were sharing a pair of electrons on both of these stage places where you see a single line, but these electrons were not shared evenly between the different components that make up this molecule. Rather, the electrons spend more time around the oxygen atom than they spend with the hydrogen atom. So because the electrons spend more time with the oxygen than they spend with hydrogen, the negative charge of electrons introduces this end of the oxygen of this molecule, the oxygen end of a molecule, being slightly more negatively charged. Remember, electrons carry a negative charge. The electrons are spending more time around the oxygen, so the oxygen end becomes slightly negatively charged overall. Whereas the hydrogen end, it has less time that the electrons hang around at this end because the electrons are spending more time away from the hydrogen. This end becomes slightly positively charged. So we're seeing that water molecule is actually a polar covalent, has a polar covalent bonds. So the electrons are shared unequally with the different components of this water molecule. Now, because we have this unequal sharing of the electrons and because we have this polarity within the water molecule, This is the reason why we're able to establish an attraction between the different water molecules in relation to other water molecules. So remember in life that negatives and positives attracted each other. So here we have a single water molecule. I removed all that nitty-gritty and I simply drew a blob for oxygens and hydrogens. And we're seeing from this blob that the oxygen end is more negative, whereas the hydrogen end is more positive if we look at it on a molecular scale of a single molecule. Well, again, I've illustrated same thing here, just in a smaller scale. And if we add other water molecules around this water molecule, we'll see that they spontaneously start to organize in a way where pluses and minuses are as close to each other as they can be. So we're starting these different water molecules starting to form bonds with each other. And these bonds are between the positively charged part of a single molecule with the negatively charged part of another molecule. And these bonds between different water molecules are known as hydrogen bonds. So it really is because of this polar nature of the water, when we end up seeing that water typically tends to kind of have this this property that we kind of give for water that's really important and very useful for us. And this property is that water is great solvent for many things, thanks to the polar nature of of the uh, of the water molecules. So many things dissolve in water over time. Here I simply took some M&M candies with the food coloring on the surface of them, and you'll see over time, if they're in water, they will dissolve in water. And we'll see this actually in life, that most things will dissolve in water. That's why water is known as a great solvent in chemical reactions. Another property of water that we see, thanks to this attraction of water molecules to other water molecules, is that water molecules kind of tend to stick together. You can even take a drinking glass and fill it above its rim, and still the water won't start always flowing over if you don't go crazy, because these water molecules were attracted to each other. They're holding on to each other rather than letting themselves collapse and run over the ledge of this drinking glass. This force of water molecules kind of forming this surface that tends to stick together. So when water molecules are attracted to other water molecules, is known as cohesion. Cohesion simply refers to the attraction of water molecules to other water molecules. Another property of water is that we have something known as adhesion. Adhesion rather means and refers when water molecules are attracted to other polar surfaces that we have. So here, for example, you see humidity droplets or water droplets on surface of a plant. And during early mornings, it's common to see this after a night. And this is because these particular water molecules now are sticking really hard to other polar surfaces, such as this leaf of a plant. This is actually what gives us something known as a capillary action. When you take a glass jar or any jar really full of water and you put a really thin straw in there, this straw is made of typically of a glass and it's really thin. Water actually has a tendency of climbing up in this straw naturally to a certain distance because it's clinging on to the walls of this thin glass straw. So these forces, water being attracted to other walls of polar surfaces, is known as adhesion, and that gives us rise to this capillary action that we also see. We also see that water has a tendency of forming high surface tension. That has to do everything with the cohesion that we just discussed about how water molecules were attracted to other water molecules, and we have these bonds between these water molecules. This gives us the property that the surface of water can actually be rather hard. So a lot of bugs, for example, utilize this as they walk on the surface of the water. They don't sink in there because of this high surface tension of the water. We see that also if you've ever done a belly flop to a swimming pool, really the surface tension of water is kind of hard. If you hit the water as a flat surface, it can really feel as a hard surface to fall in. So for that reason, when you do swim jumping, a lot of the time we try to break that surface tension of a water by hitting, for example, feet first or hands first, breaking the surface tension before we continue into the water. This is a reason why in certain instances surface of a water can be just as hard as a concrete. Let's think of, for example, planes doing an emergency landing on the water. You would just think that, oh, not a big deal, it's just going to float there and nicely water is going to be cushioning. No, you actually have to hit the water in a certain angle, and it can be a hard surface, and that can cause issues. Like I said, the belly flop, I think, is a good example of that. We also see that water is great at storing and releasing heat. So a lot of the time, water is where heat builds up, heat gets stored, and water is also a mass from which the heat gets released over time. This is really an explanation why we often, as a mankind, enjoy living on the coastal areas, because during the hot daytime, the water, these big bodies of water that we have on a coastal region, tend to just bind some of that excessive heat so that the temperatures don't rise quite as high. And overnight, when the temperatures drop and it gets colder, the water slowly releases some of that heat that it bound. So the temperature fluctuations are much lesser on coastal areas where you have big bodies of water next to that area. This is why we see here in Arizona that we have big temperature variations between the very hot summer days of our dry Arizona climate, and then during cold nights, temperatures can really drop quite low because we don't have that water to bind the heat and release the heat as needed. We also see this concept of water having a great ability to bind and release heat in how we use water. For example, your blood is mainly made of water, and we can transport now heat from one body part to another body part with that water in the blood. So we use that adaptation a lot. We saw how water could take different forms: solid ice, liquid water as we see in a glass, and then the vaporous form of steam water, vapor. That's another characteristic of water that definitely merits the mentioning. We do use water as a transport media in many living organisms. I mentioned earlier on blood as a way to transport materials around our body, and you'll get to talk about that on your BIO202 class in quite an extent. But it doesn't just have to be blood. It can be, for example, in plants, simply water that we use to transport nutrients from the soil to the leaves, through the trunk, root system, and through the trunk. So water is a great way of transporting materials because it was a great solvent. It had a capacity of dissolving a lot of things. So you'll see how these things all connect together. I hope that that makes sense and that helped a little bit of explaining why water is really considered so essential and so important for life. In fact, we find that most living things are mostly made of water. So this is why we really look for signs of water when we are searching for life outside our own planet, for example. As a review, I wanted to mention two words. We have sometimes molecules that are known to be hydrophilic, so they're attracted to water. And we have also molecules that are known to be hydrophobic, so they avoid water. How I think of this is that if you have a phobia of something, you have a fear of something, you try to stay away from it. If you are philic towards something, you're attracted to it, you love it, you try to be close to it. So we see again these water molecules and the properties, polar nature of water molecules being very important. And where we see this hydrophilic and hydrophobic concept is, for example, when we look at the phospholipids. Phospholipids are what our cell membranes are made of. So our cell membranes are made of two layers of phospholipids that spontaneously arrange in a way that the hydrophilic tails of the phospholipid are facing towards the center of the cell membrane, whereas the hydrophobic tails, I just want to make sure that I said it correctly. So hydrophobic tails of the phospholipids are facing towards center of the cell membrane, whereas the hydrophilic heads are facing towards outside of the cell membrane, so towards close where the liquid around or inside the cell is going to be at. We'll get to talk about this concept a little bit more a little later. Another question that sometimes comes up is that why does ice float? And that has everything to do with the chemistry that we just had a look of. So in a liquid form, water molecules are actually able to be packed much closer to each other. But when water takes a solid form, it freezes, these water molecules form these crystal-like structures, and these crystal-like structures really are a little bit further, cause the water molecules to be a little bit further apart from each other than what we see elsewhere. So because these water molecules are a little bit further away from each other, the same amount of water will take a larger volume when it's solid, when it's frozen, whereas liquid water, the same amount of water takes a smaller volume. So basically, water expands as it freezes. And now, since the water expands as it freezes, it causes that solid water, the ice, is slightly lighter than liquid water, which is slightly more dense. Because remember, you had more water molecules packed to a smaller volume in a liquid form, whereas you had the same amount of water molecules taking a larger volume because there was these water molecules having to be a further distance apart from each other to form this crystal-like shape. So that's why ice is slightly lighter. And if ice is slightly lighter, it's going to float on the surface of liquid water. This is also why we see sometimes, for example, garden hoses bursting during freeze nights. So there might be a little water left into the garden hose, but as the night comes and it freezes, it has to expand. And if it has nowhere else to go, it will rip apart that garden hose. This is why, for example, putting drink bottles to a freezer to make them cold really quick can be dangerous if you leave them to a freezer for too long of a time, because as the liquid starts to solidify in the bottle in a freezer, it has to expand, and if there's nowhere to expand in that bottle, what will happen eventually? That bottle will burst. So that's the explanation why we can have sometimes a mess in our hands when it comes to that. Let's have a look of also the concept of pH scale really quickly. pH scale actually tells us the relative concentration of hydrogen ions in a particular solution. So it's a mathematical formula tells us that how much hydrogen do we find in that solution. And pH scale runs all the way to 14, 7 being the middle value, anything below 7 being acidic, which means that there's lots of hydrogen ions in that substance. Values higher than 7 tells us that they're basic solutions, so there's less hydrogen ions in these solutions. I do want to point out that pH scale is not actually directly proportional, so you can't say that pH 8 is twice that of has twice that of hydrogen ions in comparison to for example, pH 4. That is not how it works because it is actually a logarithmic scale. So it's not directly proportional. We have certain chemicals that we can put into solutions, and these chemicals, thanks to their chemical properties, will end up binding to anything that will change, any other chemicals that would change the pH of that solution. So they essentially bring back the pH of that solution to a normal range. So buffers are these chemicals that help us to neutralize drastic changes of a pH of a solution. And in my BIO201 labs, you would have definitely explored different chemicals buffering abilities. So really, what we end up seeing, I guess, is that the chemistry that we just saw is important. And we saw that chemistry of carbon and hydrogen is really important when we talk about the chemistry of life, because carbon and hydrogen being so prevalent, so important for most living organisms. If we look at a single carbon atom, what we see that carbon atoms typically have 4 electrons on their valence shell, which make them very reactive. They're really actively trying to fill that valence shell and get to that stage where they would have 8 electrons on their valence shell. So carbon as an atom, carbon as an element, is very, very reactive. And what often happens is that we end up seeing that carbons naturally tend to bind with others, form these covalent bonds where they reach that state of having full valence shell by sharing some of the electrons. What we're seeing here is actually we're seeing the same number of carbons in all of these configurations that we're seeing, but the carbon has taken very different, the carbon backbone of a molecule has taken very different shape. So even though there's the same number of carbons, we can form many different kinds of molecules out of that. These are known as various different isomers of this same carbon backbone that we have for these molecules. So isomers have the same chemical formula. They have the same number of substances, but they take physically different shape when we look at the molecule shape. A lot of the organic chemistry, so the materials that have a living origin, a lot of them do have this carbon hydrogen backbone, and to this carbon hydrogen backbone then we add additional functional groups that define how those molecules behave. And I've listed some of the most important functional groups that we have into this table, and functional groups typically always have the kind of similar effect on how that molecule will behave in different chemical reactions. So having an understanding of different functional groups is a little bit outside the scope of what I try to for us to accomplish here, but I just want you to be aware of that. That can be really handy when we're trying to understand chemical reactions. And I actually have provided this list of different functional groups on your handouts for this week's materials on the canvas. So if you're interested in that, that's absolutely available. Now let's move away from the pure chemistry as such and remain on the level of molecules, but look at really big molecules, and let's look at big molecules that are most essential for life. So you remember that molecules were made of 2 or more atoms that came together to form this larger chemical unit that we had that had an overall neutral charge typically. So there are certain molecules that we commonly find in life that are very, very important for us as we're studying life, and especially as we're studying human organisms. These molecules are known as our macromolecules. And there's 4 of them that we'll have a quickly look of today on this revision. We'll have a look of carbohydrates, we'll have a look of lipids, we'll have a look of proteins, and we'll have a look of nucleic acids. So these are our 4 important macromolecules that we see in life that are going to be essential for us to consider. And as we start this discussion, I want to just make sure that we have some shared language, we have some shared basic terms. So let's first talk about monomers and polymers. Whenever we have a single unit of something, it's a monomer. So for example, in this example, it would be a sugar unit that we see, a single simple sugar. One of them monomer. If we have multiple of them that line up together to form a more complex sugar, we talk about polymer. Poly referring that it's made of multiple subunits that made up, in this example, the complex sugar that we're seeing. So having monomers and having polymers is going to be essential as we're covering the material that's related to this chapter. And now we need to start thinking about how monomers can become polymers or how polymers can be converted into monomers. Well, there's 2 mechanisms, 2 processes that can take place. Here in this initial picture, what we're seeing individual monomers. There's this individual blob that's made of a large yellow blob with 2 blue blobs at the end of it. And these individual monomers can join together to form a polymer that you see at the bottom of the screen, these yellow blobs that are joined together by oxygens. And how does this happen? Well, when you have monomers that join together to form polymers, this is usually a result of a chemical reaction where water is released as a byproduct. So because we're forming something bigger from individual monomer subunits, we're forming this polymer, we talk about the synthesis. We're making something, we're synthesizing something bigger from individual subunits. And how we're synthesizing something bigger is by process of removing water from as part of this reaction. So we are dehydrating as we're synthesizing monomers into a polymers. So monomers, individual subunits, join together to form a polymer, and as a byproduct, we're left with water. So you saw we had our reactants and we have our product. Reactants were the monomers, product is going to be the polymer and the water. This is known as dehydration synthesis. This can work also the other way around. We can have a large polymer initially, and we break this polymer apart into individual monomers. So when we're breaking something apart, if we often talk about lysis, we're breaking a large polymer into small individual monomers. There's lysis happening. And how we're able to break apart this large polymer into individual monomers is with the help of water. So by adding water to this reaction, that's where the word hydro comes into play. So in hydrolysis, we take a large polymer and we break it apart into individual monomers with the help of water. So the reactants in this reaction would be the polymer and water, and the product would be monomers. So this kind of a reaction is known as hydrolysis. So we can see this, for example, if we take a glass of water and put sugar cubes into there. These sugar cubes then can dissolve into water, but if we evaporate all of the water away from a glass that contains sugar water, these sugars will then crystallize. So really the water is the force that drives these reactions that we're seeing here. Let's talk about enzymes a little bit. So we could have various different kinds of chemical reactions as we saw earlier on. And chemical reactions would happen anyways. But by adding an enzyme into a chemical reaction, we're assisting that chemical reaction to happen. How this enzyme assists chemical reactions can be in numerous different ways how it happens. So here I have a graph. The reaction runs over time towards some direction. But for a reaction to start to happen, we need to reach a certain energy level so that the reaction then happens. That's the solid green line that we're seeing here. This energy level can be rather high before the reaction will happen. That needs to come to play. Now, if we add an enzyme into this reaction, the enzyme can bring down the activation energy so that the reaction happens much more easily with the lesser initial energy investment needed. That's just one illustration of how enzymes can work. Enzymes can also make chemical reaction much quicker, so to speed up that chemical reaction that would normally happen anyways, but by adding an enzyme to that reaction, now, rather than it's taking its sweet time to happen, the enzyme makes this reaction happen much quicker. It can make this reaction happen more easily, it can make it happen more effectively, more completely, in many ways. Remember, enzyme is a chemical or is a general term for something that assists in a chemical reaction. We don't specify how it assists, it just assists. And one way how I describe enzymes to my students is shown here on the bottom of this diagram. So here we're seeing a chemical reaction with this green block and this chemical reaction would be that this green block gets broken into two pieces. This would happen anyways over time. So we have a larger green block, and over time it will break into two sub-pieces. This will happen regardless whether we have enzyme in the reaction or not. However, if we add an enzyme to this reaction, and the enzyme is symbolized by this yellow blob that we're seeing here, this enzyme helps us to accomplish this reaction. And in this case, it could be, for example, making it more quickly. So enzymes come to assist. They have an active site where the reactants bind to. The enzyme can change its physical shape during the reaction, but when the reaction is over and we are left with our products, enzymes return back to their original shape and can be reused to assist in further reactions that will take place in the future. One typical enzyme that we see a lot of the time is a catalyst. Catalysts are enzymes that speed up chemical reactions. And sometimes there is this misconception that all enzymes would be catalysts. That's not the case. Catalyst is an example of an enzyme, but many enzymes are catalysts, and catalyst simply is an enzyme type that helps to make the reaction happen much quicker. I hope that that makes sense. Now that we have a grasp of these basic terms, let's return back to these molecules that we talked about and to these biological macromolecules, most important large molecules that we need for life. So let's start by looking at our carbohydrates. And when I talk about carbohydrates to my students and ask what carbohydrates are, students often come up with a really good list of things like bread and pasta, rice, corn, potatoes. Those all contain high amounts of carbohydrates. But remember, carbohydrates can be also other types of carbohydrates that we get from diet, such as leafy green vegetables are a good source of carbs as well. What carbohydrates are used for in the body is that we use them as a source of energy, so source of fuel for our body. They provide the raw materials from which also many things are built from. So I think that in a way, because many of us like our carbs, In a way, it might be an evolutionary remnant from the time when we really wanted to ensure that we could get in as much energy into our body as possible. So we have this preference for carb-rich food. We really enjoy it. These days, we don't have a shortage of food in many parts of the Western world, but we still have this natural innate affinity to consume foods that are carb-rich, energy-rich. So that might be an explanation why we're so enjoy of the carbs. I do want to mention at this time also fiber in the diet. Fiber is anything that we can't digest, that we can eat and consume. That just simply passes through our digestive system. So you might ask, why do I need to eat then fiber in my diet? Why, what good would that do if I'm not able to extract any energy or any raw materials for my body from that fiber? Well, fiber plays an important role in diet for few different purposes. First of all, fiber adds bulk to the food that we eat. So your stomach will physically be scanning, is it full or is it empty, based on if the stomach wall lining is stretched or whether it's loose, meaning that it's empty. Well, by adding more fiber to the food, you will feel full physically more earlier and for longer time. So you will kind of be able to get that sensation of being happy and being full with the amount of the food that you've consumed much more easily. Another thing that fiber does that's really important for our digestive system is that fiber helps us to push the material along this digestive tract. So it kind of scrapes and helps to move material along the way. Sometimes my students tell me that fiber helps you to poop. Yes, it is the material that passes through the digestive system that doesn't really get used. It helps to move materials along. So that was just kind of a side note what I wanted to mention about fiber. But let's stick with our carbohydrates on our discussion. So carbohydrates come in many different forms based on their complexity. The most simple carbohydrates are known as monosaccharides. They're made of simple single sugar unit. We can have more complex carbohydrates where we have two sugar units joined together. These are our disaccharides. And then we have very complex carbs where we have multiple subunits joined together. Well, now the question might be that which kinds of these should I eat? What is the best option? Well, really in the consumption of the food that you eat and consumption of the carbohydrates that you get from your diet, what your body does is that it breaks these carbs over time. As you need more energy, it keeps breaking more carbs into components. So complex polysaccharides are broken down into disaccharides and eventually monosaccharides, and then the energy is accessible for your body as needed. This is really why eating simple sugars as a main source of diets, although might not be ideal, although it gives you those sugars easily available very quickly. So you kind of get a sugar rush as soon as you eat simple monosaccharides in your diet. The problem is that then those sugars have been burnt off and there's not much left. So often we get this crash of energy after consuming simple sugars as a source of energy, simple monosaccharides or even disaccharides in our diet. So if you want to store long-term energy in your body that's available for when your body actually needs that energy, it might be beneficial to eat complex carbohydrates, so polysaccharides. And this way, your body can slowly keep breaking apart these complex carbs and they get broken down when there's a need for energy to be released in your body. So that's why we really recommend that if you want to get the maximum effect and you want to have energy available for your body when you most need it, you probably should consider eating complex carbohydrates. I did want to mention an example of a polysaccharide, just that's kind of an interesting one or a fun one. That's our chitin. This is what most exoskeletons of bugs are made of. So remember, bugs don't have an internal skeleton like we do have. I often describe chitin as a kind of the exoskeletons as almost like an armor around a bug. Their bones are around their body. And these are example of polysaccharides. I sometimes think we see these sprays that we use against the bugs to get rid of bugs or kill bugs. What they do, they actually dissolve these polysaccharide exoskeletons of bugs, so that causes their death. I sometimes think about what a way to go when your bones dissolve and you just are left as a blob. So I don't know ethically how to feel about that. But I wanted to mention the polysaccharides and the chitin as an example of a specific type of polysaccharide that we often see in animals and insects forming their exoskeletons. So, like we discussed earlier on, many people do recommend that if you're consuming carbohydrates, you should aim for more complex carbs. Some examples of those are like whole wheat bread, multi-grain breads, things like that. Because if you're going to have those multiple steps of breaking apart these carbs, they are going to stick around in a body for a longer time and be available when you need them. If you eat really simple sugars, they are tasty for sure, but they don't tend to stick around. So you get that sugar spike, a high amount of energy available, and then it's consumed, and that's it with that. So you do what you want with that knowledge, but that should explain the complexity of carbohydrates as a dietary source of energy. Let's move on in our review and let's have a look at lipids a little bit as a biological macromolecule. When we talk about lipids, we're talking about fats. Some of the sources of lipids, if I ask from my students that they typically list, include oil, butter, lard, things like ice cream, cheese, things like that contain high amounts of lipids. But remember, there's other sources of lipids in a dietary sense as well, such as fish, avocado, nuts, seeds, olive oil, that are considered as a good sources of healthier lipids. When we talk about lipids, lipids are highly concentrated long-term energy. And that's why, again, I keep coming back to this thing that maybe as a species, we're really attracted on consuming lipid-rich food, lipid-rich diet, because we get a lot of energy to our body really, really quickly. Lipids also are insoluble in water, and we find lipids being used in life on surface of certain organisms. For example, on surface of plant leaves, you might find lipids to kind of protect that structure. On surface of certain fur coat of animals so that the water doesn't protrude through, you might have a lipid coating on those animals as well. If we look at the lipids, we look at the fats, what fats are made of. They are triglycerides. Triglyceride tells us that it's made of a single glycerol molecule where we have three fatty acids attached to. So triglycerides are what we're talking about when we talk about lipids, when we're talking about fats. And in a chemical sense, triglyceride is a combination of one glycerol and with three fatty acid chains attached into that. We can see these same concepts that we saw earlier in our discussion, that through a process of hydrolysis, we can break apart triglyceride into a single glycerol and three separate fatty acid chains. So we're breaking this polymer of a triglyceride into smaller parts by using the process of hydrolysis. We also could put together three fatty acids and a glycerol into one triglyceride by a process of dehydration synthesis, where we're joining these subunits into a larger molecule together. This is kind of a nice reminder of what we've already learned. But I want to shift our focus to fatty acids when we're talking about the fats. I think these fatty acids merit a little bit more consideration from us. There's different kinds of fatty acids. We have something that are known as saturated and unsaturated fatty acids. Saturated fatty acids are made of single bonds between these carbons that form the backbone, hydrocarbon backbone of these fatty acids. Saturated fatty acids, typically in dietary sense, are found as solid in room temperature. These include things like butter and lard. So they tend to be solid in a room temperature. They are made in a chemical level of single bonds between the carbon atoms. We do know from research that saturated fatty acids are associated with a higher cardiovascular disease risk. So they're considered as not as good source of fats for our body. So we're trying to move away from consuming saturated fatty acids. Unsaturated fatty acids instead have at least one, if not more, double bonds in their chemical structure. A double bond causes this unsaturated fatty acid to have this kind of a kink in its shape if you really look at the shape of this molecule of fatty acid. Typically, if we look at unsaturated fatty acids as a source of dietary energy, unsaturated fatty acids are found liquid in room temperature, such as oils, and they are considered as a healthier option in terms of the health consequences of them. So there's a lesser association with cardiovascular diseases that we see when we talk about unsaturated fatty acids in your diet. So that's the general gist of the difference between saturated and unsaturated fatty acids. However, there is one more group that's a man-made variation, because we started seeing that these saturated fatty acids were not that good for us, even though they were sometimes considered as more tasty and attractive than unsaturated fatty acids. Back in the day, someone thought that, well, maybe we can use this chemistry for our benefit somehow. And what happened is that we started producing something that are known as hydrogenated fats. These are also known as trans fatty acids or trans fats. These are produced as a result of an industrial process where we take these liquid fats, we take these unsaturated fatty acids, and we add hydrogen into their structure to convert them into more solid substances in a room temperature. So we're chemically altering these oil-like substances to appear like more solid substances in a dietary sense, so that we would have the idea was that we would maybe have a healthier option that's still as tasty and attractive. And this is where these imitation butters, margarines, things like that became very, very common and very, very used. We're now finding some evidence that even though the idea behind hydrogenated fats was probably well meant and well intended, they do have a risk of introducing bad cholesterol to our body, which causes narrowing in arteries and can become a problematic in that sense. So we're generally encouraging people to steer away from hydrogenated fats based on our current best understanding of these different fatty acids and these man-made alterations. When we think about these hydrogenated fats, like I mentioned, margarines are a good example of that. You can also look at the production process of margarines, which is an interesting topic on its own. When we end up seeing that margarines need to be produced by man, and that process includes using heavy metals. That process includes producing a mass that might not be as attractive visually, so we bleach the product before it becomes a margarine and becomes ready for consumption. So there's some concerns and some discomfort that some people have about the whole idea of margarine and production process of that. But I'll let you make your own judgments about that, how you feel about it. But I did think that it's an interesting topic to explore. So earlier on, I mentioned phospholipids, and now that we're talking about fats, that's a good time to circle back to that. Phospholipids have a hydrophilic head part and hydrophobic tail ends. These hydrophilic head parts are attracted to water, whereas hydrophilic tail ends really try to stay away from water. And when we take a bunch of phospholipids and let them just be spontaneously together in a liquid, they will spontaneously organize themselves into structures such as cell membranes. So cell membranes or plasma membranes are found surrounding cells. We often describe cell membranes as phospholipid bilayers because there's two layers of phospholipids that are tightly packed next to each other that form the cell's membrane. I wanted to mention really quickly steroids. Steroids are biologically active organic compounds with four rings arranged in a specific configuration. They are important for many processes in our body, such as signaling molecules, for example, in endocrine system, and they are worthy mentioning when we're talking about this concept. We convert cholesterol into steroids, for example, but you don't need to consume cholesterol-rich food. Your body will produce all that you need. The next group that I wanted to talk about proteins a little bit as a macromolecule. Proteins, good sources of proteins include things like milk, egg whites, beans, red meat, tofu, things like that. One of the interesting things is that proteins don't really get stored in your body. They have to be available for your body from the diet when you need a source of energy. And we typically use proteins when there's no other source of energy available. So we don't have carbs or we don't have lipids. That's when we turn to proteins as a source of dietary energy. We also see that proteins are what our muscles, for example, are built from. So the building block material for our body. If you do exercise a lot and you train heavily, but you're not getting sufficient carbs, you're not getting lipids, eventually your body will seek for a source of proteins from your own structural proteins. So you will start burning off your own muscles. That is something that we see sometimes happening. This is really where these no carb diets are planning on, that if we don't have carbs, we start burning lipids. So we start burning fat tissue. But if there's not sufficient fat tissue for energy, we might have a problem that then we start consuming our own body, the muscles as a source of energy. So you kind of need to know what you're doing when you are doing dieting and going to the extremes. I wanted to mention in terms of proteins, there's many different kinds of proteins. Proteins serve many different purposes. There are structural support proteins. They play an important role in metabolism, transport proteins on the cell membranes, for example, in body's defense mechanisms, regulation, movement generation, as we saw when we talked about protein in terms of structural material for muscles and so on. The big thing that we saw that if we're talking about proteins as macromolecule, you do need to get proteins as you need them because they don't get stored. So that's why sometimes in a gym you see people who have their protein shakes with them so that they try to insert that if they're training, they are also providing their body as much protein as possible for that purpose. Proteins are polymers of amino acids, and we do have different kinds of subgroups. And again, I think if I didn't already uploaded it, I will upload it later on. But there are different kinds of tables that helps you to look at these side groups that we find in these molecules. When we talk about proteins, we can study proteins on various different levels. So proteins are essentially just chains of amino acids, but then these can be looked at rather than drawing them out as a chemical formula in much more three-dimensional method, three-dimensional form as sheets, or then bending into these complex three-dimensional structures. So we can look at primary, secondary, tertiary, and quaternary structure of a protein based on how complex we consider it to be. Sometimes my students talk about proteins and they see in their textbook a picture of Nicole Kidman, and that's probably a little old reference. What that refers to is the fact that proteins really are a good example of how a small change in the chemistry can have also a drastic change in the physical appearance of a protein. So at the time, we know that hair is made of protein. So at the time, Nicole Kidman had straight hair, but she took a perm, and that perm, that chemical reaction of these proteins, changed the physical shape of a protein as well. We see the impact of proteins also when we look at, for example, red blood cells, which are normally these kind of flattened biconcave discs squashed from the middle. But if we have an error there, we might end up with sickled red blood cells. So that's another thing that we sometimes see when we discuss proteins. So really, like I said, this explains this order of carbs, lipids, proteins, what's your preferred order for the body to consume these as sources of energy. The last macromolecule that we have left to discuss is nucleic acids, and I'm going to keep it a little bit briefer. So nucleic acids, Na, are really what our DNA and RNA are made. So both DNA and RNA are important in terms of either storing genetic information in our DNA or as converting that genetic information, making a copy of it and translating it into proteins, as we see in the case of RNA. Let's have a look of a nucleic acid a little bit. Here we have a structural illustration of that. So we have our sugar and we have our phosphate group. These sugar and phosphate are always consistent from one nucleic acid to another. We will always find these both structures. So often we talk about sugar phosphate backbone of the DNA and RNA. They are the continuous part. And in addition to that, in a nucleic acid, we have a varied part that can, the base that changes, that can vary. It gives us those different bases, adenine, guanine, cytosine, and thymine, or in case of RNA, rather than having thymine, the uracil. So these are really the varying parts which code for that message in the DNA or RNA. So that letter code, that's the instructions for what kind of protein to make based on a single gene. So that completes the review of chemistry, and then larger scale of having a look of the macromolecules. Let's have a look of quickly a life on a level of a cell as well, since we're here together. Cells are really the smallest of things that are capable of surviving by themselves, existing by themselves. So we often talk about cells as the fundamental basic unit of life. It's the smallest structure that's capable of existing and living on its own without need of another structure to be part of it. Cells are typically small, We're talking of as microscopic structures. We have some cells that we can also see with naked eye, and there are few exceptions of cells that can be really, really long, like nerve cells in your spinal cord. But in general, cells are small. But we need to know about cells because, like I said, all life is made of cells. So when we're studying of cells, we end up ourselves having to use microscopy to study these small structures. Light microscopy allows us to look at a lot of things. And if we can't see it with a light microscope, which uses light to go through that sample and study it that way, we might need to recruit a second type of microscope known as electron microscope, which instead of using light shoots electrons and uses that to visualize the tiny particles that we're studying. Here's a nice scale of showing how far you can see with the naked eye. When you recruit a light microscope, you start to see more of the cell, but even the smallest cell organelles are so small that you can't see them other than with an electron microscope. So we have different ways of studying stuff in our study of sciences of the small components that make up life. So I mentioned earlier on that cells are small by default, and the explanation why cells are small has to do with the fact that there's a concept known as surface area to volume ratio. As the cell size grows, the surface area of the cell grows at a smaller rate than the total volume of the cell. And we want to have as much surface area as possible so that we have a chance of doing that exchange of materials in and out of the cell. And also, the distances in a cell growing too large could be a problem for the cell's own functions. There are a few ways how we can increase the cell's surface area. That's by adding additional folds on the surface of the cell. So we see membrane folds or microvilli, those small hair-like structures growing out, which are meant for increasing the surface area of the cell. One way how I explain to my students why cells need to be small when it comes to the metabolic functions within the cell itself is to use an example of, think of a gas truck. Gas truck's job is to transport gasoline from one place to another. However, if the distances grow so big for that gas truck to travel, it needs more gas to do this journey, so it starts to eating from its own load. So in order for our cell to be able to transport components from one cell part to another cell part, we want to make sure that the distances don't grow too big, so we have this effective transportation of materials. When we're studying cells, we're talking about a field of cytology, whereas if we study cells that are close together, serve a similar purpose, are similar, we start to talk about tissues, and study of tissues instead is known as histology. Earlier this week, you had a chance to have a look of how to prepare a sample of a bacterial cell, I believe, and that gave you a little bit of experience last week, of simulation of how these processes are done in a lab setting. Sometimes I get students asking me that, well, how did cells first come to be? Where did cells appear? Nothing just appears out of nowhere. Well, based on our best understanding at the moment, the cells and the various different parts that we find within the cells, the cell organelles, likely the early part was that we had a simple organism that entered into a cell, and there was a beneficial symbiotic relationship between these organisms. So that's how cells first appeared. We have many different kinds of cells. Typically, we can classify most cells into two groups, into prokaryotes and eukaryotes. Prokaryotes were the first ones to evolve. They're much more simpler, and they're also physically much more smaller. There is a cell membrane, but there are no actual cell organelles within this prokaryotic cell itself. So the DNA is floating free within the cytoplasm of a prokaryote, and there are no those separate cell organelles found within the cell either. Eukaryotic cells instead are much more larger physically, and they are much more complex because we start to see these membrane enclosed specific compartments within these eukaryotic cells. So for example, DNA is closed within the nucleus. So there's a cell membrane within the cell itself within which the DNA is housed. Same goes for all other cell organelles that we'll see as well. And these specific compartments is really what is important when we talk about these eukaryotic cells and are a sample of an animal cell. Let's have a look at different parts of a cell, and let's start with the cell membrane, so plasma membrane. You remember earlier on I referred to plasma membrane as a phospholipid bilayer. By that, I mean that it's made of individual phospholipids, and there's many of them. And phospholipid had the hydrophilic head part and hydrophobic tail part. We see that the phosphate group forms the head part and the fatty acid chains to form the tail part of a phospholipid. And we see that that's really where the word phospholipid comes from the phosphate group and the fatty acid tails. And we had two layers of phospholipids, so phospholipids that are tightly packed next to each other in two layers that formed the cell membrane, with the head parts that were hydrophilic facing outwards and tail parts that were hydrophobic facing inwards. I think that we already had a discussion about the heads and tails there, so I'm just gonna keep going onwards. Within the plasma membrane, within the cell membrane, we often see also other things embedded in there. So it's not just phospholipids. We often have, for example, proteins embedded into cell membranes. Proteins are many different kinds of proteins. They can serve many purposes for a cell. They can be channels for the passage of materials in and out of the cell. They can also actively transport materials in and out of the cell as pumps. They can play a role in recognizing, for example, one cell recognizing another cell. They can also be receptors, as we see in case of hormones, for example, using certain kinds of proteins as receptors for those hormones. They can serve enzyme-like functions, assisting in reactions, or they can be junctions, connections from one cell to another, helping passage of materials or messages from one cell to another. Often when we talk about cells and cell membranes, we talk about fluid mosaic model of a cell membrane. By that, we mean two different things. First of all, we mean with the word fluid that the cell membranes are constantly changing and moving. So all the diagrams that you see tend to be a little oversimplification. So they're very dynamic structures. The proteins, for example, are constantly moving around, flipping their sides, and so on. And also the fluidity of the cell membrane refers to the fact that there's many materials moving across these membranes as well. The mosaic instead refers to this fact that it is really made of many different elements and many different components, just like a mosaic art piece is made from those little pieces of ceramics or rocks that then together form something greater, a bigger picture together. So that's what I mean when I talk about cell membranes as a fluid mosaic model. Plasma membranes also could include, we wanted to have a large surface area, so they could include adaptations that give us more surface area by introducing various different kinds of folds or villi to increase the surface area of the cell membrane, so as much exchange can happen between inside and out of the cell as possible. When we look at the cell and we look inside the cell after we've now covered the cell membrane, we see that the inside of the cell is filled with cytoplasm. This is all the material inside the cell except the cell nucleus. This is kind of a jelly-like fluidy material, mostly made of water. There's also some salts and so on in there that really fills the cell giving its kind of its shape, but also kind of being the site where most of these activities of the cell can take place. There's a lot of metabolic activities taking place, waste processes happening, and also the cytoplasm provides kind of the matrix holding the different cell organelles, which we will review next, on their place. So you can kind of consider that it really is what gives the cell its shape and keeps everything on its place. Another structure of the cell that I want to start by discussing is nucleus. Nucleus is where the DNA of the cell is housed at, so the genetic information. We can study the material within the nucleus in a greater detail. We see that we have this string-like mixture of DNA and RNA and protein that can in certain conditions take the shape of a chromosome in certain part of the cell cycle as it condenses and wraps around itself. DNA was basically all of that information and parts of a DNA that code for making particular proteins. Their kind of instructions for making particular proteins are known as genes. How I often describe this to my students is to think of a cookery book. You have many recipes. That cookery book is your DNA, and you take parts of that cookery book, individual recipes. Those recipes would be genes, and you use those recipes to make dishes, which would be proteins. So you're never going to have all of the genes active at the same time. You're never going to cook every single recipe from a cookery book at one time. That would not make sense. You choose the genes that you want to use. When we see nucleus, nucleus is again enclosed structure. We have a membrane surrounding the nucleus, actually a double membrane. So the DNA is housed inside there. And DNA never leaves the nucleus. RNA instead can travel in and out of the nucleus. Here we're seeing a microscopic view, electron microscope view of the wall of the nucleus's wall. You'll see that there's this small opening, nuclear pores, through which materials can travel. Like I said, DNA stays within the nucleus, whereas RNA can enter and leave this membrane. And RNA is really what we use to produce the protein. So how I describe this to my students is to think of DNA as a very precious book that we have in a library. Most libraries have some sort of a special collections department, or they have original manuscripts, and those are something that you can't check out from the book or from the library. They're so valuable, they're so precious. What you can do though is that you can come to the library and to the special collections department and you can study the book there. You just can't take it home with you. You can take notes of the book, you can take pictures, you can sometimes take photocopies even. And this process, this is DNA, this special book that remains always in the nucleus. However, what you can do though, I said you could take notes of that special book. So we can make a copy of a DNA. This would be our RNA. Our RNA is a copy of a DNA strand. So we're copying every base for that section that we want to make a copy of. We're getting all the information. And then you can take this, and this RNA can be taken out of the nucleus of the cell. This process of making a copy of the DNA, making an RNA copy of the information in it, is known as transcription. So just like you can transcribe in the olden days when they had secretaries that transcribed what the CEO told and then typed up the letter, that process of making a copy from DNA into RNA is known as transcription. Now, RNA could leave the nucleus of the cell, and as it travels within the cytoplasm, it will find a ribosome. Ribosome is used to convert the message stored in the RNA into actual functional protein. So a ribosome attaches to the RNA and brings amino acids based on the code of 3 bases at the time and attaches them one after another, producing this chain of amino acid. This chain of amino acids now becomes a protein, and that's the actual functional workforce of what we learned from that gene of that section of the DNA. So this process of converting the message from RNA into a protein is known as translation. So now we're not just making a literal copy, we're actually giving it a meaning. So we're translating the genetic code into something useful that we can then utilize. Let's talk about mitochondria. We can find mitochondria in the cell. These are traditionally described as the powerhouse of the cell. That's where the conversion of the chemical energy, we convert energy into ATP, which is the chemical currency of, or we convert carbohydrates into ATP. That's the chemical currency of the cell and cellular processes. This process happens at the mitochondria and requires oxygen and produces as a byproduct carbon dioxide. For the longest of time, we thought that all of the production of ATP happened in the mitochondria, but we're finding out that it happens also in other parts of the cell, but mainly still within the mitochondria. Within mitochondria, you'll notice that it's again a cell membrane or membrane enclosed cellular structure, and it even has these folds inside. These folds inside are known as cristae. What's interesting about mitochondria has its own DNA, and actually this DNA of mitochondria is inherited maternally, so that adds a little bit to the discussion if we look at the DNA issues. Only in plant cells will we find chloroplasts. Chloroplasts are cell organelles that are responsible for the process of photosynthesis, so converting carbon dioxide, water, and solar energy into sugars, as we see here. And as a byproduct, chloroplasts, as they convert solar energy, carbon dioxide, and water into sugars, they beneficially for us humans produce as a byproduct also oxygen. So we find chloroplasts in plants and also in algae. They're an important structure for the process of photosynthesis, which I think you've learned about before. Here we have a diagrammatic representation of a chloroplast. We see the stroma, the fluid inside the chloroplast. We see these disc-like sacs piled on top of each other. They are known as thylakoids. And then you have the granule, which is the stack of these sacs on top of each other. Another structure that you see in the cells is known as endoplasmic reticulum. Endoplasmic reticulum is kind of an outgrowth network of membrane tubes coming from the nucleus of the cell, and they can extend to many directions within the cytoplasm. There's two types of endoplasmic reticulum. There's smooth ER, in which case these membrane tubes don't have anything on their surface. They're just nice and smooth in terms of their appearance, and they play many different roles in the terms of the cell's functions. We also have rough ER, and in case of rough ER, there are ribosomes that have attached to the surface of endoplasmic reticulum, and these are the sites where we are producing proteins from the RNA. So ribosomes were responsible for the production of the proteins. So two types of ER: smooth ER, where there's nothing on surface, and rough ER, where we have those ribosomes attached to the surface. Another structure that I wanted to mention in terms of the cell and cell structures, Golgi apparatus. This is kind of like a stack of folded membranes, if you wish to describe it as such. And I often describe them to my students almost as if they were like a distribution center of a cell. So they receive materials, sort, repackage those, and then send them out of the cell as well. So an important part of a cell as well. We have various other sacs-like structures that we find within the cells: vesicles, lysosomes, and vacuoles, especially in the plants, large structures. Important, either storing materials, moving materials, things like that. Another cell structure that we see and that's important in a cellular division of or cell division is our centrioles. This is a pair of cylindrical tubes that are typically found near the nucleus in animal cells, and they are mainly made of proteins. Their role is to provide the spin attachment point for the spindle during the process of cell division when the DNA was replicated and divided into two poles of the cell. So that's something to note there. Really, I wanted to also highlight the cytoskeleton of the cell. These are microscopic tubes and filaments forming a network within the cell and cell cytoplasm, kind of anchoring things on their place, forming a scaffolding, giving the cell its shape, and also providing movement pathways for the materials to travel across the cell. So an important part of the cell. If we look at the cells and we compare animal cells to plant cells, some of the biggest differences that we end up seeing that animal cells had this plasma membrane that was kind of a more malleable, is not as rigid. A cell can kind of change its shape and be squashed and move a little bit to an extent, whereas plant cell walls are made of cellulose, so they're much more rigid, much harder, help plants to take these shapes that plants have, provide support for that as well. Yeah, and we of course saw that, for example, chloroplast only found within the plant cells and so on and so on. I wanted to mention the connections between different cells. So that might be important as well for us to see that cells do interact with other cells. We can have three main types of cell junctions from one cell to another. This kind of a tight junctions where we have multiple proteins connected side by side, forming almost like this zipper-like appearance of a Ziploc pack, bringing these two different cells cell membranes tightly together. We can also have something that are known as desmosomes or adhesion junctions. These are really anchoring spots on both sides of the two cells, cell membranes, and many as filaments that come out of these anchoring points. So they're very, very strong attachment points in that sense for structures within the cell as well. And we often also find gap junctions between the cells. These are kind of protein channels that allow the movement of materials from one cell to another cell. So materials can pass, messages can pass nicely between two cells. So those are some of the many different kinds of junctions that we end up finding within the cells. We're almost at the end, but not quite. And what I want to do next is to discuss two more concepts that I didn't really have a chance as much to discuss that are important for us. And I'm going to jump out of this presentation. Let me just stop sharing. And let me move here. And I want to discuss a couple of more concepts that are really important as we are looking at the basics of the language that I want us all to be familiar with. I wonder if I can bring this here to make it a little bit easier for us to follow along. Let's see if we can make this work. So you should see the little paper that I have in front of me. And let's discuss two reactions that are going to be important for us to have an idea and appreciation of. So we're going to discuss about two types of reactions that we see in the body. These are catabolism and anabolism. In catabolic reactions, what we have these individual atoms that have joined together to form a larger molecule. And you remember that these connections were really important, these bonds between individual atoms. As we have this large molecule and it breaks apart during catabolic reaction, we're left with individual atoms, but by doing so, we're also releasing energy. So this is really what happens in life pretty much all of the time. So all large structures tend to naturally gravitate towards breaking apart. And as they break apart, these bonds that we saw forming the molecules, as they're broken apart, they release energy that we can then use to drive processes in the body. These kinds of reactions are known as catabolic reactions that we see in the body. Let's have a look at anabolic reactions a little bit. In anabolic reactions, we have again individual atoms, but if we add energy to this reaction, we can join these individual atoms together to form a larger molecule. So I guess the big take-home message from here is that we're seeing how taking individual components and putting them together to form something larger, a larger molecule, that process required an energy investment from us. And that's what we know as an anabolic reaction. So I hope that that helped to clarify those two terms and two concepts together. Another thing that I want to mention, and let's see if I'm able to move there, that might have came up in your discussions or in your review of key concepts this week. I know it was a lot of material, but like I said, I think it's largely revision of familiar concepts, is the concept of exocytosis and endocytosis. So let's have a look of what exocytosis and what endocytosis is. So sometimes we have a need to move large amounts of material in or out of the cell. In exocytosis, here we have this cell and we have our nucleus within the cell. And let's say that we have some material here that we want to get out of the cell. We want to send it out of the cell. So how we do it is that we bring this small vesicle close to the wall of the cell with the materials inside there, and these two cell walls fuse together, and slowly we can open this side as it fuses so that the material can exit the cell. In an endocytosis, we're talking about a cell basically engulfing some material. And again, we have the nucleus here. Here we have some material that we would really like to take into the cell. So the cell membrane kind of opens up and almost makes like this little blob that can then separate from the cell wall, forming a vesicle, thus carrying the material inside the cell. So now it's coming in. Exocytosis out of the cell, endocytosis into the cell. These are often what we can see, for example, in immune system when we talk about phagocytosis. So those were two final concepts that I just felt that were really important for us to have covered and mentioned. And let me jump back to the presentation. Just give me a second. Let's see if I'm able to share my presentation again. And if also able to get the camera on. I think it's always nice to see who's talking to you. So I think that at this point, we've really gotten really far on our review of the material. And really the last thing for us would be to discuss about the homework. But this session has taken much longer than I had anticipated it to take. So I think that we're just going to wrap up at this time. The homework, the quizzes for chapter 2 and chapter 3 really follow the material that we have covered before. It really is very similar format that we've already become familiar in earlier work that we've done for this course. So there's no curveballs there. I think it's largely revision, so it should be kind of a nice chapter or nice week, even though it's a lot of material. I do think that it is familiar material. And like I said, the big goal is just for all of us to end up to the same place and feel comfortable of what we've covered and where we're at with our studies. So with that, let me jump out of sharing this view. And I'm gonna do one more thing. If I'm able to share my screen here. Right now, you should be seeing my Canvas course, and you can see that for this week, we have 3 chapters, even though it might seem like a lot to cover. Really, like I said, a lot of this is things that you already know. I have your textbook available for you, but also some supplementary materials like lecture videos. And handouts that might help you as you're revising the material. I'm asking you to complete the 2 quizzes, chapter 2 and chapter 3 for this week's work. There is no requirement to do additional work, but if someone wants to challenge themselves or feels a little bored or wants more complex concepts, there is more that you can complete there, and you can submit them through this second part of the Want More a section of the learning module. If you do any of those, I'm always happy to give extra credit points. But remember, you just need to collect 90% of the course grade and you get an A. So doing those weekly quizzes is often really the best way to accomplish that. And that brings us to the end of everything that I had planned to cover today. I know it was a longer session, so depending on whether someone shows up today to the afternoon session or not, I might just provide this recording for you. I'm not going to do it twice unless someone joins me, but I hope it's been helpful. Remember, these are completely optional. These are completely optional resources. There is no expectation that you absolutely have to do them. All you need to do is do your weekly homework and exams and tests, and you're going to be well on your way to succeeding on this course. Like I said, this week and last week have been a little bit of revision of things that you are probably already very familiar with. Bear with me. This has been important for us to establish a shared understanding and shared ground of where we're at. And moving forward, starting next week, we actually get to the meat of the matter and we get to discuss various different body systems, one system by the time. So I'm going to wrap it up here for today. I hope you have a very good week. If I don't see you or hear from you earlier on, remember, I am here to help you. That is a big part, an important part for me of my job. Even though this is an asynchronous online class, it doesn't mean that you have to do things alone. All you have to do is let me know how I can assist you, and I will definitely help you. I often get good questions from students that, oh, it would help me if I had this or that type of a diagram or explanation. So I'll gladly add them. That's, for example, how these cell diagrams were added to your handouts last semester. So let me know how I can help you. I want you to succeed on this class, but I also want you not to stress about it. I really appreciate each and every one of you for being part of this course. And by that, I'm going to wrap it up and wish you a very good rest of the week. Thank you. Bye.